We're going to take a look at solving linear inequalities in one variable. Now, the good news is we've already solved linear equations in one variable, so we really just need to look at what does inequality really bring to the party here. Well, we know what our inequalities are. We've seen these things in the past. It's these symbols. And generally speaking, we tend to read this as less than, greater than, less than or equal to, or greater than or equal to. So if we had a statement like this, we would read this as 2 is less than 7. So it's an order operator. It kind of tells us what order things are on the number line. However, you generally don't want to give these things specific names, because what happens for some reason, what if we wanted to read this in the opposite direction? Now, from left to right, it's 2 is less than 7. If we were to say that that's strictly the less than operator, then we would say 7 is less than 2. Well, that's not right? 7 is greater than 2. So depending on which way you read the inequalities is which way that you actually say that the order really is. Now, it's basically going to be the same thing we saw when we were solving linear equations, kind of like x plus 2 is equal to 3. The only difference is when we solve something like this, generally we get a finite number of answers, right? We get x equals 1 solution. But think about it, if we were to change it to something like this, and we'll see how to actually do this, we would end up with something like x is less than 1. Now in this case, there's an infinite number of solutions to every one of your inequalities. Because how many numbers are less than 1? Well, there's an infinite number of them. Well, that's a problem when we're trying to represent them. So what we're going to take a look at right here for a second is how to represent your answer. Just by solving a problem, we're going to get an algebraic answer. We're going to take a look at what it looks like on a number line. And then we're going to use something called interval notation. And last, set builder notation. All right, so let's start with this. Let's say if we have x is less than 4. Let's say we actually solved the whole problem when we got down to this algebraic statement. X is less than 4. Now, there's an infinite number of answers that are less than 4. If we wanted to put those on the number line, the easiest way to do that, go ahead and draw yourself a number line. Now, since we're only comparing the values we're looking for to 4, you really don't need to put all the numbers on the number line. Just since we're only comparing it to 4, you can just put a 4 on there. Now, where are the values that are less than 4? Well, those would be all the values to the left over here. So I'm going to be shading to the left. But what about the number 4 itself? Well, 4 is not less than 4, so 4 itself is not part of the answers. But we can get as close to 4 as we want to. 3.9, 3.99, 3.99, so on and so forth. The way that we're going to represent that is with an open circle. That means we can get as close to 4 as we want to, but we just can't actually include it. Now we're going to shade over here. So that's a visual picture of all the numbers that are less than 4. For interval notation, here it's always going to be we're going to state the answers from the smallest number that's an answer, comma, to the largest number that's an answer. Here's what I mean. When we're looking at this, what's the smallest number that we have shaded? Well, since it goes to the left forever, it goes all the way over there to negative infinity, comma, and what's the largest number we have shaded? Well, again, that's really tricky because there is no largest number. It goes 3.9999 on forever, so we can't really put that there. So what we say is we're going to go right up to 4. Now we're going to surround our interval notation with either parentheses or square brackets or some combination of the two. Now if you have parentheses next to a value, that means that is not included as part of your answer. If you have a square bracket next to a thing, it is part of your answer. So let's say, is negative infinity part of our answer? Well, it'd be really easy to say yeah, because you say it goes all the way over there to negative infinity. But you can't ever get to an infinity, so you never get there. So infinities always get parentheses next to them, no matter what. Now in this case, since the 4 is not included, we're going to go ahead and put a parenthesis next to the 4 also. So interval notation, again, saying the same thing that we had here. It says, we're just showing a picture of all the numbers from negative infinity up to 4, not including it. here we're saying we want to start from negative infinity, go all the way up to 4, and of course not including either one of them. Now set builder notation, now a set is just a group of numbers. Generally we denote a set with curly brackets, something that looks like this, and generally we put the things in the set separated by commas. The things in the set are called elements, so this set has 3 elements in it. That's the way we normally represent a set. However, when you have an infinite number of numbers or things in your set, it gets a little bit more tricky to list them. Now, one way to do it would be something like this. If we just wanted the whole numbers from 1 on out, we could go 3, 4, and do ... Now, that set there has an infinite number of things in it, and we can represent it with the ... because we've established a pattern. Unfortunately, when we're dealing with all the real numbers on the number line, there's no way to set up a pattern like this. So the way that we're going to do set builder notation looks like this. Of course, you're going to start by doing the set bracket thingies. Now we're going to talk about, according to our algebraic expression, our variables x. So what x's are we talking about? Well, the way that you write this is you put x and you put one straight up and down bar like that. That actually stands for such that. I'll write that in a second. So we only want the x values such that the x's are less than 4. So the way that you would read this whole notation is the curly brackets means this is the set of all x. The straight up and down bar means such that, and then everything after that, this piece over here, this is the condition. The condition that you're saying has to be true. So curly brackets means we're talking about a set of all x values as long as those x values are less than 4. Okay, so there's set builder notation. Real easy way to think about it. It's just going to have the curly brackets, the variable you're talking about, straight up and down bar, and then this piece right here, this piece should always be your algebraic answer. Okay, let's try a couple more of these so we can see how to represent our answer. So if I said x is greater than or equal to 7. So here again, we're only comparing the x's to 7, so that's really the only value I need on the number line, so I can put a 7 right there. Now in this case, the x value can be greater than or equal to 7. So now 7 is part of our solution. So instead of an open circle, I'm going to put a closed circle at the 7. Now we're looking for the values that are bigger than the 7, and on the number line, we know that those are the values that head out to the right. All right, so once we have a graph, now we're going to take a look at interval notation. What values do we have shaded? Well, we started shading at 7, comma, and we went on forever, so this goes from 7 to infinity. Now this time, since we are including the 7, we put a square bracket next to the 7, and infinities always get parentheses. All right, so set builder, let me go ahead and get our words out from underneath here for a second. For set builder notation, again, this is going to be the set of all x such that we said x had to be greater than or equal to 7. All right, so these are normal inequalities, and for every single one of your problems, you're going to want to give your answer in all four forms. Well, you're going to get the algebraic from solving, so you kind of already have this one. But once you have an algebraic answer, you're going to want to always try to practice graphing it using interval notation and set builder. Now, I know they all say the same thing, and it says, well, why would you say the same answer 4 different ways? Well, you're just practicing the different ways of expressing an answer. That way, if you see a different one of these in the future, you understand what the author's talking about. The last kind of one we want to talk about is something called a compound inequality. Compound inequality is an inequality that has more than one inequality in it, or a sentence. So it'd be like 4 is less than x, which is less than or equal to 10. So you see in this case, the x is being compared to more than one value. In this case, x is, like we read to the left now, x is greater than 4, but it also has to be less than or equal to 10. Now, since we're comparing x to 2 different values here, we're going to have 2 different values on our number line. We have a 4 and a 10. Now, x is strictly greater than 4. So that doesn't have the equal sign, so that gets an open circle. X is less than or equal to 10, so it can be 10, so we're going to close the circle at 10. Now you can see here, just visually speaking, what values are we looking for? We're looking for the values that fall in between those two. So we're going to shade from 4 to 10. All right, interval notation, where do we start shading? We start shading at 4. We go all the way out to 10. We're not including the 4, open circle. We are including the 10, closed circle, so we put a bracket there. Now, set builder notation, again, since we're talking about x's, we'd say this is the set of all x's such that, and then our algebraic answer that we would have got is 4 less than x less than or equal to 10. And there's your set builder notation. All right, so every problem that we're going to do, we're going to want to represent our answer with all these different forms. Now, we've talked about how to represent our answer, but not actually how to solve these type of inequalities. The good news here is since they are linear inequalities in one variable, we're going to do exactly the same thing we did when we solved linear equations in one variable. Almost. So, to solve linear inequalities in one variable, you solve exactly the same way you solved linear equations in one variable. Well, almost. So the good news is we're going to follow the exact same series of steps we did for linear equations in one variable, except if you multiply or divide both sides by a negative, you need to flip the inequality. Okay, so we're going to use the same steps we solved for solving linear equations, except if we multiply or divide both sides by a negative, we're going to flip over that inequality. Now, the reason that you have to do that, let's go through this real quick, is we're still going to use our golden rule when we're solving equations, right? When we solve equations, what do we do to one side, we got to do the other side. The reason that we're able to do that is because the statement still is true as long as you do the same thing, right? That's a true statement and it's an equation. If we were to add 5 to both sides, we would get what? 8 equals 8. Still true, so we're allowed to do it. And you're allowed to do anything you want. You can divide both sides by -4, you get -2 equals -2. It's still true. Well, does the same thing happen when you're dealing with inequalities? If you have 8 is less than 10, well, that's true. And as long as we do the same thing to both sides and it's still true, we're allowed to do it. So I could add 4 to both sides. If I add 4 to both sides, I get 12 is less than 14. Still true, so you can add a value to both sides, which means you should also be able to subtract something from both sides. If you subtract 6 from both sides, you get 6 is less than 8. Now you can multiply and divide, you can see the same thing would happen, but watch what happens, let's say you divide both sides by -2. Well, that gives you -3 is less than -4. And you can see on the number line, there's 0, we go here, there's -3, -4. Since the -4 is farther to the left, it's smaller than -3, so this is no longer true. So what would we have to do if we wanted to divide both sides by a negative, or multiply, same thing would happen. To keep this true, we would have to take that inequality and flip it over. Now it's true. See, because the negative really means the opposite of. So if you're taking two numbers and we're doing the opposite of them, well, the inequality needs to be the opposite also. So just a quick little reminder, just all you're thinking is I'm going to do the exact same steps I did for linear equations, but if I multiply or divide both sides by a negative, I'm going to flip over that inequality. All right, so let's try one or two of these. So the directions here will probably be a little bit more than solve. It'll probably be solve, graph, use interval notation, and set builder notation, because they want you to show all the different ways that you can do this. So let's start out with a fairly simple linear equation. Let's do less than or equal to 8x minus. All right, so like always, we want to classify this. This is a linear, because all of our variables are the first power. Inequality, because we have an inequality. So you say, well, I know how to do that. I'm just going to follow my steps for a linear equation. First step says clear grouping symbols. I don't have any. Next step says clear fractions or decimals. Don't have any, but you do it the same way if you did. Move all your variables to one side. Now, good news, bad news here. Again, just like with equations, it doesn't matter which side that you move your variables to. However, most students tend to like the variables on the left with equations, and especially inequalities. So I'm going to go ahead and move all my variables to the left. So I'm going to get rid of all of them on the right by dividing both sides, or by subtracting 8x from both sides. So I get negative 4x minus 6 less than or equal to negative 4. Since I got all my x's on the right, I need to move everything that doesn't have an x to the other side, less than or equal to 2. Last step, divide both sides by whatever's in front of my variable. So I'm going to divide both sides by 4 here. But since that 4 was a negative 4, that means that this inequality has to switch around. So it goes that way. So if you multiply or divide both sides by a negative, you got to flip that around. Now, of course, reducing that gives us negative 1/2. All right, so you notice we did the exact same steps as we did before. We just got to watch out for this inequality flipping if we multiply or divide both sides by a negative. Now, once we have this answer, let's go ahead and see if we can graph it, use interval notation and some set builder notation. Since x is only being compared to one number, the negative 1/2, that's the only thing I really need to put on my number line. If we read this, x is greater than or equal to 1/2. So we can include the 1/2 in our solution, so we put a closed circle there. This means x is greater than, so we want the values that are bigger than 1/2, that would be over here to the right. Interval notation. We start at 1/2, we go all the way out to infinity. We're including that 1/2 so it gets a square bracket. We never include an infinity, so it gets a parenthesis. Set builder notation. It's the set of all, here we're talking about x's, the set of all x such that x is greater than or equal to negative 1/2. Okay, so there's how we're going to represent our answer. So the good news is almost not a lot of new material here. It's all stuff that we've kind of seen before, except for how to represent our answer. Let's take a look at those compound inequalities, though. Now remember, the example I gave you looks something like this. I don't know, 5 less than or equal to x less than 20. Right? That's what a compound inequality looks like. Now the difference here is when we go to solve these, we're not trying to get x on a side all by itself. We're trying to get x alone in the middle. So that's our goal. Get x, or whatever letter it is, alone in the middle. Now the good news here, at least for this course, is x is always going to start out in the middle, and you're not going to have any x's on the left or the right when you first start. And the good news is, since it is linear, our linear steps are still going to work exactly the same, except for what's our golden rule? Whatever we do to one side, we have to do to the other. Well, since we're trying to isolate the x in the middle, we're going to change our sentence just a little bit. We're going to say, whatever we do to the middle, we got to do to both sides. Or another way to think about it, you kind of think it has 3 sides, a left, a middle, and a right. So whatever you do to one side, you got to do to all the sides. So I'm just going to say, whatever you do to the middle, you need to do to both sides. Okay, so that's kind of how we're going to change our golden rule here just a little bit. Let's take a look at one of these. Let's say if I have 3 less than 2x minus 4 less than or equal to 10. All right, this is a compound inequality, and it's linear because our variable is to the first power, compound because we have more than one inequality. So when you see these, you say, okay, I want to try to get that x alone in the middle, but you're still going to follow your steps for solving a linear equation. Step 1, clear any grouping symbols. We don't have any. Step 2, clear fractions or decimals. We don't have any. Step 3, get all of your variables to one side. Now, remember, we got to change that a little bit. All of our variables we want alone in the middle. So get all of our variables in the middle. That's done. Get everything that doesn't have a variable out of the middle or to the other sides. So here, to get rid of this -4 that's in the middle, I would add 4 to it. But whatever we do to one side, I have to do to the other sides. So when we do this, we get 7 less than 2x less than or equal to 14. Last step, divide both sides, or all the sides, by whatever's in front of your x. So we divide everything by 2. Now, just like before, if we divide by a negative, we got to flip over both inequalities. But this time we divide it by a positive value, so the inequality stays the same. So this is 7/2 less than x less than or equal to 7. Okay, so now we got x all alone in the middle, which means we're done solving this compound inequality. Let's go ahead and see if we can graph it and use interval notation and set builder notation. All right, since we're comparing x to 2 different values, we need 2 different values on our number line, 7/2 and 7. For reading this, this says x is greater than 7/2. So it can't be 7/2, so that gets an open circle. X is less than or equal to 7. So x can be a 7, so that gets a closed circle. Now again, visually you can see the x is falling in between these, so that's what we're going to shade. Interval notation, what values are our answer? Well, the values go from 7/2 over to 7. We're not including the 7/2, so it gets a parenthesis. We are including the 7, so it gets a square bracket. Interval notation, set builder notation, it's the set of all x values such that, and just write down your algebraic condition. So this is 7/2 is less than x less than or equal to 7. All right, solving linear inequalities is exactly the same way we solve linear equations. All you gotta do is watch out for, if you multiply or divide both sides by a negative, you need to flip over those inequalities. Now you do got a little bit extra work, and it's really just practicing the different notations. Every time you solve an inequality, you want to practice graphing it on a number line, using interval notation and set builder notation.